Pat, I'm excited of having you here at NextSilicon offices in Israel. Is it your first time in Israel?
Well, not quite my first time. This is probably trip 100, 110 to Israel. As many know, many visits to Israel due to Intel. And visited much of Intel Israel, worked for me, so I was here, twice, 3 times a year for 30 years, right, with Intel. And of course, this trip, right, the pleasure of seeing NextSilicon, but maybe the main reason is to be at Technion and getting an honorary doctorate tomorrow at Technion. So,
congratulations.
Well, thank you. Super exciting, and we all know that Technion and Intel have had just an incredible relationship over many decades to really making Israel the tech nation that it is today.
We have spent the past 4 hours here in the offices. We walk around. The amount of excitement that people has towards you and everything that you have done in Intel, and specifically in Intel in Israel, is tremendous. I don't know if many know, but Intel was one of the cornerstone of the Israeli high tech in general. I think that most of the employees at NextSilicon in the hardware section were hardware employees that used to work for Intel and started companies like Mellanox, later to be acquired by NVIDIA. My company got acquired by Mellanox, later be acquired by NVIDIA. So it's all connected, and I think that many people owe you, as one of the early sites here in Israel, a big congratulations. I spent my youth, programming in x86. And then when the 386 came, and you had the 66 and 67 prefix in the opcode in order to use the large 32-bit register, I was excited, and meeting you in person, especially after all my history, was a great excitement. So thank you for doing that. And maybe I would like to hear a little bit of your voiceover about how you see CPUs, what's the role inside the compute ecosystem.
Yeah, and such a wonderful history that I've had in computing, and being in the 286, engineer number 4 on the 386, engineer number 1, an architect of the 486, and then the design manager of the 486. That x86 instruction set is near and dear to my heart and soul. And but it never really was about the x86 or the instruction set. It was always about the workload. It was always about what you ran on it, and Windows, and then Linux being those operating systems that enabled all the application stacks, and whether that was the the first DOS on Windows, whether that was the first multimedia, whether that was the database, whether that was the cloud software, it was always enabling the software stack. And for that, the x86 was a seminal, right, enabler, because so much software was run on it. It wasn't whether it was good, it was whether it ran. And then being compatible, right, was this magic of being able to have generation by generation compatibility, because it takes years to develop a mature software stack. And how can you take that software stack forward? If you're compatible and you're faster, it was like magic. Right, and that was really the heydays, if you could, the magic period of Moore's Law, where we just kept making the CPUs better and better, both microarchitecture and process technology. So, this period of the history of the CPU was sort of magic, right, in the sense that Moore's Law, the process technology kept getting better, but we also were making the microarchitecture better. Run more software, make the software run faster, advancements, and clocks per instruction. All of that just sort of came the magic period of Moore's Law and the 386, 486. What a joy it was to be in the middle of that.
I think it was a tremendous run of the processor in x86. As you said, we enjoy so much from process innovation, going down into the nanometer, better frequency, and then the nanoscaling came, and frequency halted, and power consumption increased, and GPUs suddenly came. What do you think was the trigger that caused people that design massively parallel application. Because CPU is always good for serial execution, for the operating system. We will always need a CPU. Most of my use cases when with AI, not anymore, but most of the use cases is based around CPU. So we are going to have them for life. But what do you think was the trigger that causes people to look for new architecture, GPU specifically, when the CPU performance got into a barrier?
Yeah, and it was always about the workload, right? And if the workloads were on the CPU just kept winning more workloads, right? And driving more of that ecosystem. And I remember many a discussion between Jensen Huang at NVIDIA and myself on scalar versus throughput and, the work that they were doing. And the only volume deployment for the GPU was graphics, ergo graphics processing unit, right? No magic, right? But, and I'll say Jensen, and I applaud him for this in NVIDIA, they stayed true to that mission. We're just going to increase compute density. We're not going to worry about, the speed of execution or how, branches were being done, and more of the silicon area was being spent on non-execution, branch buffers and target buffers and buffers, because essentially there wasn't more parallelism to harvest in the CPU, and that's where the GPU really started to emerge. And it was this throughput, increasing density of compute, creating more general purposeness to the software stack through CUDA and the other steps that they were taking. And then, of course, the magic moment was AI, right? Where it was just not a little bit better, it was 10x better to run on the GPU. And then as AI became a mainstream workload as opposed to this little niche thing off of the side, the GPU broke out of graphics and really became a GPU. And today, the history of computing is different because of that.
I think that, if we are looking on a CPU core, then the CPU processor, 2% of a CPU core is allocated for the ALUs, and everything else is for out-of-order execution, reorder buffer, all the queues and the queues, in order to optimize, as you said, latency, how fast we can run instruction per clock. And with GPUs, you have smaller cores, more of them, more throughput oriented.
Lots of threads, right? Management of state is minimized, but it is all about compute density.
But one of the downside of a GPU is, as you mentioned, or what now is known as the software mode, is the CUDA, or domain-specific language. You couldn't take a CPU code, a general purpose code, a C, C++, Python code, and simply run it on a GPU. It will not run in an efficient way because of cache coherency, the way that memory laid out. In order to squeeze the performance, you need to know exactly what you're doing. CUDA was invented back in the 2006. And it took around a decade until users were adopting the GPU itself as the native compiler to run their application. And I think that NVIDIA was super smart, super thoughtful, how they gave away GPUs for free for university education program. It was, think about other CPU alternative like ARM, and a decade or 2 decades until they got in adoption. This is a GPU which was way, way more painful. Now, Jensen said that he saw that a small percentage of the application runs the majority of the time.
Yep.
And trillions of dollars were spent for general purpose acceleration, and it just failed because if you could do that, that will be called a CPU. So he decided to go after GPU and CUDA, and it all started with CUDA. Mm-hmm. So my ask to you is, what do you think about CUDA, software mode, domain-specific languages?
Well, obviously we've seen it being successful now, But as you say, it took a decade plus of maturing that software stack because it was ugly, it was hard, right? Because all of the software energy was over here and general purpose compilers and operating systems and lightly threaded workloads. That's where all the energy was, databases, user interfaces. We're very accustomed to that. And figuring out how to program in highly parallel ways was hard, right? And it just took a long time for that to develop. But then important workloads, obviously high performance computing was much more parallelizable. And then, of course, AI, machine learning was the breakthrough workload because it isn't just, can I get the application there, but do I care about that application? And all of a sudden it was this idea that I had a domain specific language that was dramatically better in an important domain. And to me, that was the thing that moved, CUDA from this fairly niche, ugly language to increasingly becoming a mainstream computing paradigm for the industry. But of course, now we have these two worlds, CPU and GPU. What do you think? Can we fix that and bring those back together?
Well, first of all, I believe that there is going to be a new era of compute. The main reason is that GPU performance plateaued. And why do I say that? Because we are seeing GPUs with increased performance, but also increase in power consumption.
Yeah, right. And if you don't improve power, performance, efficiency, you're not improving. You're just sucking more power, right, into higher density footprints and increasing power.
Exactly.
Power density, power per rack, power per data center.
And you need to normalize everything for dollar. So it's power, performance, and dollar amount that need to be assigned. I think that, and we are seeing GPUs getting to 3600 watt.
Yeah, which is just crazy. I mean, it wasn't that long ago where a 400 watt CPU was like, man, right? Can you push that back to 300 or 350 watts? But now we're talking about thousands of watts for a GPU. What happened, right?
So in order to show more performance, you are making the die bigger and bigger. You move to chiplets, so now you have four full Retica chiplet altogether aggregated to 3600 watt. And like 4x more performance with 4x power consumption, that's a slight increment. I do believe that the big next generation compute company will be the one that show more performance, like 10x more performance, quarter of the power consumption. But I think that one of the most important aspects on doing all of that is not by inventing a new CPU or a new GPU. Because if someone can develop a new GPU, a new tiny cores that can do all of that magic, probably NVIDIA with the amount of resources or AMD or Intel that they are spending will figure it out. New novel architecture, like NextSilicon, a smart algorithm that understand what matters, reconfigure the chip in a 20 nanosecond in order to give the actual kernel that run the majority of the time, the bigger space of the die. That's the way that the future goes. But we are not stopping there. It's not about the 10x more performance with quarter of the power consumption. CUDA is a fact of life. You have CPU application that run in C, C++, and for supercomputing industry, even Fortran. The ability to have a software solution that is drop-in replacement, meaning it can run GPU code, it can run CPU code out of the box, that's mandatory in order to ease the transition into this new architecture. And one of the key aspects that we have placed here at NextSilicon is the ability to be agnostic to the software stack. You can run CPU application written in Fortran, or you can run AI workload, VLLM with custom CUDA kernel. We can run them all. Different architecture, smart runtime solution that understand and reconfigure the chip. This is what we are all about.
And I'm excited about it, and excited about the progress the team has made. And I see that, there's two dimensions of innovation, to me, they're exciting. This idea that, we're moving past CPU, GPU, in creating highly performant, underlying architecture that's driven by data flow, which is ultimately the limitation, right, of how dense we can make computing. So bringing that together in a much more flexible underlying architecture, and of course we have RISC-V cores to run the serial code, but to me, the software innovation then that enables on top of that, because now we're redefining, because even in CUDA and GPU, or the instruction set between the CPU and the operating system, you had this hard separation between the physical silicon and the software instruction set that was coming into that hardware, and smashing that together as you're doing with NextSilicon to create, the software hardware boundary, maybe it's software or something, right, that we're, pushing those together to enable this dynamic optimization in real time, that it maximizes the hardware utilization of the running workload, right, dynamically. That's a pretty exciting set of innovations. So I see it both GPU and CPU coming together, but then the hardware level coming together with the low-level software. To me, that's sort of the magic of what we're doing here at NextSilicon, and it's really exciting to see the update today.
One of the things that you can see here when you roam the NextSilicon offices is how tightly integrated the hardware engineers and the software engineer. Like same floor, hardware design, place and route, software, low level. Because I think that one of the challenges that we had, and we have taken the long road. We spent the last 7 years building this general purpose accelerator, the one that can take CPU workload, GPU workload, smash them together to have this workload processor units. And it's needed tight integration between all aspects of software, hardware together in order to invent what we are seeing here at NextSilicon.
And I do think the idea that you're not changing CUDA, you're not changing Python, you're not changing Linux, to me, that's all the way back to the beginning of the x86, right? The magic was compatibility. You weren't changing the software stack. It takes years to build a mature software stack, to get tools deployed, to get applications optimized, and being able to say, we're not changing the software, we're just making it great with this new hardware. That's the magic of what we're talking about. But then combining it also that it's future-proofed, because I can keep upgrading that runtime software to make it more performant on the hardware that I've already installed. So to me, that's sort of the magic of not just backward compatibility, but forward compatibility as well.
100%. I mean, right now we are living in 2025, middle of 2025. Transformers is the architecture to go, talking about LLM and AI machine learning. But as we have seen over the past 5 or 6 years, neural network architecture changed so rapidly, from CNN, convolutional neural network for image classification, to transformer today, and who knows what the future holds. Having the ability to be a future-proof accelerator is important, because neural network in 27 and 28 will look in a different way. Looking at the future, you have recently joined Playground as a full-time partner. How does it feel to be a venture capitalist? How do you bet on those novel startups that will change the future of compute and silicon fabrication and more?
Yeah, and it's a thrilling time to be thinking about the future of computing, because we sort of got to a period that was sort of boring. The CPU was 400 watts, and now we're talking about thousands of watts, and we're sort of slowly incrementing the network and the memory. Wow, the doors have blown open. We're power envelopes for network designs, for size of configurations, data center spend. So everything's on the table. So we're going to create a new microarchitecture with NextSilicon. We're really moving from copper to optical, right? Power delivery networks are going to be rebuilt and optimized, but it's also new forms of computing. We're about to launch a new superconducting company. We have 2 of the premier quantum companies as part of the portfolio. I call it the trinity of computing, right? Quantum, classical, and AI all coming together. We're going to be, new materials are going to be discovered, and we're seeing that occur. And, the ability then to, I'll say, get comfortable operating in cryogenic environments near absolute zero, single photon operation. And, it really is, everything's on the table. And being able to be part of a deep tech investor like Playground, okay, this is a lot of fun. And since I've been a deep tech guy my entire career, being able to do that across a broader number of companies, not just 7x24 focused on one company, but now having a portfolio of companies, and I'm thrilled that NextSilicon is part of that, is a lot of fun. And I expect that this next phase of my career journey is going to be one of the most fruitful of my career.
I want to thank you for coming here. I know that everyone, me included in NextSilicon, got really excited and thrilled of having you around us. Thank you for all your insight and everything that you have done.
Well, I'm excited to be part of the NextSilicon team. And with my history in computing, it's a real thrill that I get to express some of that through you and the team here. We have a great thing going on, and I look forward to the bright future that we have together.